Hello, my name is Danny Solow, and I'm going to present a series of 15 lectures on how to read, understand, think about, and do mathematical proofs. These lectures are based on a book that I wrote by the name of, not surprisingly, How to Read and Do Proofs, that was published by John Wiley & Sons. And speaking of the publishers, I'd like to express my appreciation for their funding of this project, and to the Weatherhead School of Management at Case Western Reserve University for their equipment and their technical people in producing these videos. What you're about to learn is a new method of thinking, and the only way that you will learn how to do proofs is practicing. So I'll give the lectures, I'll present the material as clearly as I can, but you will need to do some practicing in order to get comfortable at this new language. I'm going to be presenting these lectures to a class of high school students. And let me put it this way, if they can learn this material, so can you. In fact, the only background material that we need for these lectures is high school mathematics. In particular, a fluency with algebra, some knowledge of basic geometry, and maybe just a little bit of trigonometry. That's all. With that introduction, let's go ahead and get started. Okay, welcome everybody to this short course on how to read, understand, think about, and do mathematical proofs. Let's start from the beginning. What we want to address first is, what exactly is a proof? A proof is a convincing argument expressed in the language of mathematics that a statement is true. Now, all of these words are important to your understanding of what a proof is. So let's start with the concept of a statement. Well, in mathematics, a statement has a very precise meaning. A statement is a mathematical sentence that's either true or false. So let's look at some examples. For instance, 1 equals 0. We know that that is
false.
False.
False. Good. How about this one? Those of you that have had geometry. The angles of a triangle in the plane add up to 180 degrees. True or false?
True.
True. Okay, so we have true statements, we have false statements. Now this next one is a little trickier. The real number x is not greater than 0. Is that true or false?
Could be either.
Could be either. Depends on the value of the real number x. That statement is either true or false, and therefore it is a valid mathematical statement. How about this one here? There is a real number x such that x equals e to the minus x. First of all, how many of you know what the value e is? Some of you know it, some of you do not know it, right? Okay, that's fine. For the moment, think of the number e as 2. Is this statement true or false? There is a real number x such that x equals e to the minus x, 2 to the minus x. True or false?
True.
True. Maybe not so clear, but it is a true statement. When a statement is true, but perhaps not so obviously true, this is why we do a proof. A proof is a convincing argument expressed in the language of mathematics that a statement is true, such as this statement right here. Proofs are typically applied to a particular kind of statement called an implication. And with an implication, you are given two statements, let's call them A and B. But what you're really interested in is proving that if A is true, then B is true. There are different ways to write this. For example, if A then B, A implies B, or A right arrow B. Mathematicians are notoriously lazy when it comes to writing, and so they've invented this shorthand notation, in this case consisting of a right arrow for the word implies. But in any case, all of these statements are the same. What's important here is for you to realize that there are really three statements. The statement A, which is called the hypothesis, the statement B, which is called the conclusion, and the statement A implies B. If you want to prove that the statement A implies B is true, then you need to know under what conditions the statement A implies B is true. It seems reasonable that the truth of A implies B should depend on whether A and B themselves are true. Let's look at the four possible combinations of truth values for A and B. As you can see, A can be true and B can be true. A can be true and B can be false. A can be false and B can be true. or A can be false and B can be false. Those are the only four things that can possibly happen. Now what we have to decide is, in each of these four cases here, did I tell you the truth? Let's take a specific example. Suppose I said to you, if you work hard in your course, then you will get a good grade. Okay, so first let's be sure we understand what is the hypothesis A here. You work hard in your course, and the statement B, your conclusion, you will get a good grade. Now what we have to decide is, in each of these four cases here, did I tell you the truth? So let's look at case 1. In case 1, A is true and B is true. A is true, you worked hard in your course. B is true, you got a good grade. So I said to you, if you work hard in your course, then you'll get a good grade. You worked hard, you got a good grade. Did I tell you the truth?
Yes.
Yes.
Yes. So let's put a T up here in this truth table in that row 1. Let's go to row 2. In row 2, A is true and B is false. A is true, you worked hard in your course. B is false, you did not get a good grade. I said to you, if you work hard in your course, then you'll get a good grade. You worked hard, you didn't get a good grade. Did I tell the truth?
No.
No. I think we can agree that in that case, I lied. And so for row 2, let's put an F in there. Let's turn now to rows 3 and 4. In both rows 3 and 4, the statement A is false. In the context of this problem, that means you did not work hard. I said, if you work hard in your course, then you will get a good grade. I did not say anything about what would happen if you did not work hard in your course. I hope, therefore, that you would agree that I did not lie when I said, if you work hard in your course, then you will get a good grade. In case 3 and 4, you did not work hard. That's not my fault. So let's give me the benefit of the doubt and therefore say that I told you the truth. And this is what we call a truth table. A truth table is a summary of the truth of a particularly complicated statement, in this case A implies B, in terms of the truths of the simple component statements A and B. In any case, this truth table is extremely important because it's going to guide us for the rest of our discussions. Okay, now just to show you how important and useful this truth table is, one approach to doing a proof, at least in theory, is to take the statements A and B and determine whether they are true or false, and use that to determine where you are in the truth table. Let's take an example. If 2 is less than 1, then 3 is less than 4. So again, we've got 3 statements here. The hypothesis A, which is 2 less than 1. The conclusion B, which is 3 less than 4. And the implication, if 2 is less than 1, then 3 is less than 4. Okay. Now, let's look at the statement A, and you tell me, 2 less than 1, true or false?
False.
False. How about B, 3 less than 4?
True.
True.
True. So A is false and B is true. Now look at the truth table, and can somebody tell me what row of the truth table are we in if A is false and B is true?
3.
Row 3. And if you look at row 3, it says that A implies B is true. And therefore, we have just done our first proof. How about that? Look at the truth of A, the truth of B, determine where you are in the truth table, and determine the truth of A implies B. Okay, let's do a second one in the same spirit, just to get the idea of how this works. If 1 is less than 2, then 4 is less than 3. So here again, we have the hypothesis A, 1 less than 2, which is what? True or false?
True.
You've already graduated from elementary school. Good. A is true. And how about B? 4 less than 3?
False.
False, which puts us now in which row of the truth table?
2.
Two.
Row 2, and therefore, A implies B is
False.
false. Okay, now, unfortunately, life is not always that easy. If it were, you wouldn't need me, and I wouldn't be up here giving these lectures. So, let me give you another example. If the real number x is greater than 2, then x squared is greater than 4. So let's look at this one and play the same game. Here we have the hypothesis A, x is greater than 2. True or false?
Either one.
Either one. You don't know. Big question mark. How about B? X squared is greater than 4. True or false? So you don't know. And now the question is, which row of the truth table is applicable? Do you know? Nope, we don't know which row of the truth table is applicable. So this, unfortunately, is the kind of statement that we are typically going to be facing, an implication. When you're faced with something like this, you can still use the truth table to figure out what to do. But that takes some clever reasoning, and I'm going to show you that reasoning. And this is where you have to appreciate mathematicians. They've done some very clever things. So let's take a look at that truth table. Here it is again. And let's say we have conditional statements A and B. So what I propose to do here is look at what happens to the statement A implies B when A is true, and let's then go back and look at what happens to the statement A implies B when A is false. So we're going to look at these two different situations. Let's start with the left-hand side. What happens to the truth of A implies B when A is false? So when A is false, can somebody tell me what row of the truth table is applicable?
3 and 4.
3 and 4. And does everybody see that in either case, what happens to the truth of A implies B?
True.
It's true. And so therefore what that means is I don't have to worry about what happens if A is false, because if A is false, A implies B is true, and I'm finished. Okay. On the other hand, let's take a look at what happens to the truth of A implies B when A is true. So, same thing. What row is applicable? Rows 1 and 2. Now, here's where you have to be careful. If you want to show that A implies B is true, which row do you want to be in?
Row 1.
You want to be in row 1. And how can you be sure that you're in row 1 as opposed to being in row 2? Well, look at B. What do you need to know about B?
It's true.
You need to know that B is true. Then that would guarantee that you're in row 1 and A implies B is true. So let me summarize what this reasoning has told us from the truth table. When you want to show that A implies B is true, you can assume A is true. Your job is to show that B is true. Any questions on this idea? Because again, this guides us through the rest of what we're going to do. The very first step in doing any proof of the statement A implies B is to be sure you have identified the hypothesis A that you can assume is true and the conclusion B which you're trying to show is true. So when an implication is worded in the form if something then something, then it's very easy to identify the hypothesis A and the conclusion B. Everything after the word if and before the word then constitutes the hypothesis A, and everything after the word then constitutes the conclusion B. Let's take an example. If n is an even integer, then n squared is an even integer. Terrific. What is the hypothesis A here?
N is an even integer.
N is an even integer, everything between the words if and then. And what is the conclusion B?
N squared is an even integer.
N squared is an even integer, everything after the word then. When statements are worded in an if-then form, like I have done it here, identifying the hypothesis A and the conclusion B, I hope, is very straightforward and easy to do. Unfortunately, mathematicians don't always write these if-then statements in such a clean if-then form. Let me give you some examples and see if you can help me to identify the hypothesis A and the conclusion B. So let's take an example here. The equation ax squared plus bx plus c equals 0 has two distinct real roots when b squared minus 4ac is strictly positive. Tell me, what is the hypothesis A here? What can you assume is true?
B squared minus 4ac is greater than 0.
B squared minus 4ac is greater than 0. That is correct. And I'd like to point something out by asking another question. What are A, B, and C?
Constants?
Constants. They are given. So this is part of the information that you can assume is true. A, B, and C are real numbers, given real numbers. Now notice that it doesn't say that anywhere in the problem. That's something that is implied by the context. And this is very typical. In these kinds of statements, Watch out for implied hypotheses, things that you can assume are true just by the way in which the statement is written. Okay, and what's our conclusion?
ax squared plus bx plus c has two distinct real roots.
Exactly. Ax squared plus bx plus c equals 0 has two distinct real roots. Everybody okay with this example? All right, let's do another example. Two lines tangent to the endpoints of the diameter of a circle are parallel. What is the hypothesis here? That you have two lines that are tangent to the endpoints of the diameter of a circle, and let's give them some names, L1 and L2. So you can assume that L1 and L2 are two lines that are tangent to the endpoints of the diameter of a circle, and what is your conclusion? In other words, what should then happen? L1 and L2 should be parallel. So again, there is a bit of an art in learning to read these kinds of statements and clearly identify your hypothesis A and your conclusion B. That has to be the first step. If you make a mistake with the hypothesis A or the conclusion B, you can forget everything else you do. It's meaningless. In this series of lectures, I'm going to make your lives easy by always writing the statement in the form if A, then B. Okay, so let's go back to what a proof is. A proof is a convincing argument expressed in the language of mathematics that the statement A implies B is true. So let's talk about convincing argument. The first question that you have to ask is, who are you trying to convince? And this is important because depending on who you are trying to convince determines how much detail you have to include in your proof. Let's take this example right here. Suppose I want to prove to you that there is a real number x such that x equals e to the minus x. Okay, so first, what is the hypothesis A here? This one you have to look at carefully.
There is a real number x?
There is a real number x. No. That's why I asked this question. You want to prove that there is a real number x such that x equals e to the minus x.
X equals e to the negative x.
X equals e to the minus x. No, that's what you're trying to prove. Anything that you're trying to prove has to be part of the conclusion.
There is none.
There is none. Other than your previous knowledge of mathematics, for example, some of you may know that e is equal to 2.718 and a whole bunch of other digits, just like pi is equal to 3.14159. What is the conclusion? What are you trying to show?
X is equal to e to the negative x?
That's half correct. X equals e to the negative x. Say the whole sentence. What is it?
There is a real number x such that x is equal to e to the negative x?
There is a real number x such that x equals e to the minus x. For this particular problem, there is no formal hypothesis other than your previous knowledge of mathematics. And what you're trying to show, that is the statement B, is there is a real number x such that x equals e to the minus x. How I do this proof might depend on who I am trying to convince. For example, if I wanted to prove that statement for a math professor, I might do something like this. I might draw a picture with an x-axis and a y-axis and say to the math professor, here is a graph of the function y equals e to the minus x. And then I'm going to lay over that the line y equals x. And you see where these two graphs intersect right at that point right there? Go down to the x-axis, and that is a real number x for which x equals e to the minus x. Now, for a math professor, he or she might look at this and shake their head and say, yeah, I understand exactly what you're doing. I'm convinced. That's a proof. You're finished. However, this may not be a convincing argument for you, high school students. For you, I have to perhaps put in much more detail than just this simple little picture. For example, some of you did not know perhaps that e is equal to 2.718, so that's part of what I have to explain in my proof. And I have to put in enough details for this to be a convincing argument for you. And this is why it's important to know who are you trying to convince. As a general guideline, when you write proofs, you should write a proof not to convince your teacher. Your teacher already knows that this statement is true. you should write a proof to convince someone else at your own level of mathematical knowledge, typically one of your classmates. Let's go back to what is a proof. A proof is a convincing argument expressed in the language of mathematics that the statement A implies B is true. All right, let's take another example here. We're going to have a little bit of fun. Here's a right triangle ABC, and what I'm going to try to prove to you is that the distance from A to B plus the distance from B to C is equal to the distance from A to C. Now that's what I'm going to try and prove. So you watch my proof and see if you are convinced. Ready? Here we go. Okay. So let's look at the distance from A to B plus the distance from B to C. And I'm going to break that distance down as follows. This red line plus this red line plus this red line plus this red line. So let's look at why that's true. The distance from A to B is this red line plus this red line. The distance from B to C is this red line plus this red line. In other words, the distance from A to B plus B to C is the sum of the distances of those four red lines. Everybody okay with that? Any questions on that? I hope that's okay. All right. Now what I'm going to do is take those four red lines and replace them with 8 red lines. And it is still true that the distance from A to B is the sum of this red line plus this red line plus this red line plus this red line. And the distance from B to C is the sum of this red line plus this red line plus this red line plus this red line. Everybody okay with that? And now I'm going to do it again, except now I'm going to have 16 little red lines. And it is still true that the distance from A to B plus the distance from B to C is the sum of the distances of all the red lines. Well, now I'm just going to keep doing that forever. And forever means that this little squiggly red line is going to eventually get right down on top of the A to C. And so the distance from A to B plus the distance from B to C is equal to the distance from A to C. What do you think of my proof? Are you convinced? Kind of. Kind of.
It is not in the language of mathematics.
That's the problem. It is not in the language of mathematics. If I showed this proof to a mathematician, that's exactly what they would say. The problem with your proof is that it is not expressed in the language of mathematics. So that's what I want to talk about next. What exactly is this language of mathematics? It's a collection of what I'm going to refer to as proof techniques. And there's an analogy here between proof techniques and the game of chess. I hope everybody's comfortable with the game of chess. Here's a chessboard with all the pieces. In chess, you have a collection of pieces, and you can describe a game of chess as a sequence of moves of the individual pieces. True? And in fact, the art of being a good chess player is to determine which piece to move where and when. Everybody all right with that? Okay. In a completely similar manner, a proof can be described as a sequence of applications of the individual proof techniques. Just like a game of chess is a sequence of moves of the individual pieces, so a proof is a sequence of applications of these individual proof techniques. And of course, the art is to decide which proof technique to use and how to use it. And let me just mention, since I'm discussing this, a proof is an art. It is not a science, just like playing a game of chess is an art. I can't teach you the creativity part of doing proofs, but what I can teach you are the proof techniques. And that's what we're going to be learning in all the subsequent lectures. That completes our first lecture, so let's make a summary. First thing is, we have learned what a proof is. And a proof deals with statements. A statement is a sentence in mathematics that's either true or false. And a proof is a convincing argument expressed as a sequence of proof techniques that the statement A implies B is true. And what we have also seen here is that according to the truth table, the statement A implies B is true in all cases except when A is true and B is false. And what that means is when you're going to prove A implies B is true, you can assume A is true. Your job is to show that B is true. And this is what we're going to be doing with a variety of different proof techniques. That completes this lecture.